Hi. Thanks very much for coming. My name's Noel. I know, and I have recognised a few people in the audience and spoke to a few people here. So thanks very much for coming. Is everyone having a good time? Yeah, it's been a great couple of days, hasn't it? So what I'm going to show today is kind of something I've tried to have a bit of fun with. I've done a few talks in the past, and they've always been, I wouldn't say they were dry, but they've always been a bit like, here's how you do something, or these are the rules you need to do to make this work, and this is how it's different in Scala and stuff like that. So I thought I'd try something a bit different and have a bit of fun, and I'll try and teach what type classes are along the way. Maybe some people in the room already know what they are. Hopefully this will give a bit of a grounding. And as always, if you're really stuck, if you're really not sure what's going on, please let me know. Like I'd rather not get to the end of this talk and people understood it than I just whiz through it and everyone has no idea what I'm talking about. So I work for a company called 47 Degrees. We've got these fetching red sweaters. We've got the booth out in the front, so we concentrate on consulting and training and development. And if that's something of interest, come and speak to me afterwards, or pop along to the booth. We're here for the rest of the day. Okay. Right. So what are we going to talk about? So the premise of this talk is trying to describe what type classes are, and I want to show this in an interesting way. So I'm going to split the talk into three. So we're going to spend a little bit of time trying to understand what a type class is and how they work. We'll then step aside and have a look at what genetic algorithms are. And then I'm going to try and mash the two together somehow. I can read that, okay. I'm going to try and mash the two together somehow, and we'll try and be a bit creative and show how the two work quite well together. Okay, so we'll start. What exactly is a type class? If you Google around, if you ask the wrong people, you get phrases like this. It's like, ad hoc polymorphism. What else do you need to know? All right, let's move on. Okay, so all right, so let's take a step back. Where do we start with this? So, like myself, and I imagine a lot of you, I came from a Java background. I've been doing Scala now for about 3 years, and before that, I was full on in the enterprise Java world. So, I thought a nice place to start would actually be back in Java land. Okay, so let's see how Java can relate to what a type class is. Okay, so if are people here familiar with Java? You come from a Java background? Yeah, okay. People not? Okay, all right. Well, hopefully this won't be too daunting. There's nothing particularly Java specific here, but I just want to show the relationship between the two. So if we look at the arrays class in Java, it's got this static method on it here. So those not familiar with this is that all we're saying here is we've got this method called sort. It's generic, parameterized on t. It takes an array of t's and something called a comparator, which is parameterized on t. And you can imagine what this does is this sorts an array. So the fact it's generic means that we don't really know what's going to be in this array. We don't know if we're going to be sorting strings or numbers or bananas or trains, you just don't know. So this extra parameter here, this is basically a rule for how to compare two things of this type t, and then that should hopefully be enough. If you can compare two things, you've got enough information there to sort them. And so the comparator has this method here called compare. Returns an integer. It takes two things of t and returns an integer. So it's probably not the best interface ever written, but you can imagine if the two t's are the same, then the integer is going to be 0. If one t is less than the other t, whatever that means, then it'll probably be negative, and vice versa, it'll be positive. And so we can use these with our own types. And so I created what we used to call pojos. And there's nothing magical here. All I wanted to do was just have something that's not in the standard library. So it's my own type. All it does is hold an integer, and we know how to compare integers. But clearly nobody knows how to sort int holders apart from us, apart from me, because I wrote it. But we want to use this sort method to do this. So we need to create our own comparator, and that would look something like this. So we implement this comparator interface. We've got compare. Look, it takes two int holder types. So we're actually being type safe here. You know that we can't compare an int holder with a string or, like I said, a banana. But we know that when we want to compare these things, we're only ever going to be using this given type here. And then this code here is what we need to do in order to compare the two. So now we can sort collections using our own type. Okay? And this would look something like this. And I'm back in the Scala REPL here. So we take an array of these int holders, and then we call sort, and of course it's mutable. But then when we go and inspect the value, we see that they've been sorted. And if we had a larger array which would fit on the slide, then it would show they sorted better. And the nice thing is here is that because we've got our own rule here, is that we get, when we sort this array, we get to decide how it gets sorted. So there's no default or there's no magic here. If we want this in reverse, we can create a new comparator here that sorts them in reverse. If we want to separate odds and evens, we might be able to do that way. We can sort things however we want. If we were doing strings, we might want to sort by length of string rather than alphabetical order or something like that. So really, the power is given back to the developer here. And actually, this itself is actually what a type class is that we've separated out our type definition from the behavior in which we want. And then we've got this method here that's saying, well, if you want to sort something of your own type, you need to tell me the rules of how to do it. Okay, so let's go back to maybe a slightly more familiar scene, and we'll look at how this works in Scala. And I'm not actually going to provide anything new here, and this example was lifted completely from Martin's paper introducing type classes into Scala. I'll put the link up there. I'll send the slides around afterwards. Okay, so we've got a trait here called ord. It's parameterized on t. It's very similar to what we just saw in Java. We've got a couple of t's here. Instead of an integer this time, we've got a Boolean. So again, might not be the best interface ever written, but we can work with it. We know if those two t's are the same, then that's going to return true. And so what we want to do, when we want to use an ord, we need to create an ord instance for our specific type. So if we want to work with integers, it would look something like this. Parameterized on int, and then we've got the parameters to our method take ints, and then we need to do whatever. Well, we know, because we're writing this instance, we know how to work with ints, and we know what to do to see if they are the same. And then once we've got this, we can use this where necessary. So we can write our own sort method here. And so I've skipped the implementation because it's not really of interest here. But so our sort method is parameterized again on t's, and we take a list of anything, but then we also have a second parameter list of orderings. And what we're saying here is that when we sort this, we've got a rule, and this is the rule to use for when you want to order lists. And so we can just use this as so. We give it a list like this, we use our ordering, and it works like it should. But a bit like the Java one I was showing a minute ago, it's a bit cumbersome. We've got this kind of backpack we've got to carry around of, if we want to order integers, we need to have that. If we want to order strings, we've got to go and find the ordering for strings and pass that into the sort method as well. So Scala provides this nice mechanism for kind of removing a lot of the noise from this method call. And so we'll do exactly what we did as before, but we're going to mark this instance as implicit. And then our implementation is the same, except this second parameter list is also marked as implicit. And then whenever we want to call sort, the compiler will try and find the ordering that's marked as implicit for our given type. And if it can find it, it will compile and run this method. Okay? And we can see this as so. And this seems to be a little bit more intuitive. I've added this type annotation here, but it's not actually strictly necessary, because the compiler can work out that we're dealing with a list of integers, and it will then go and find this int or type class instance we have. And so if there's no implicit in scope, if we're dealing with the scenario I've just shown, and we've not seen an intord for strings, what do you think is going to happen here? Any ideas? Yeah, we get a compiler error, so that's really nice. So again, there's no magic here. There's nothing going on behind the scenes. There's no default. It's not like it does nothing. The compiler's saying, I don't know what to do here. You've not told me how to sort strings. You need to tell me, and I can't carry on. So I think that's really quite nice. And basically, that's it. That's what a type class is. So if we try and make this a little bit more general, it's an implicit parameter that itself is parameterized. And this is the kind of pattern you often see. So you have a function which takes a type parameter, it's going to take some parameters, and then it's going to have some implicit parameter on the list as well. And then that's our type class. And then we know then that as long as we have an implicit of this type for this type in scope, then this will work. And once you notice this, you start to see this pattern everywhere. And the way to think about this often is you can view this as like enhancing types, is that we're effectively adding our own interface onto someone else's types. When the integer class was written, the odd class may not have been written at the same time. They are completely separate. But we now have this mechanism for any given type being able to provide functionality that works with it. So like I showed with the Java one, if we just create a type out of thin air, is that it will still work with these library functions that have been written by someone else at another time, just because we have the right mechanism and the right rules for doing so. It really is just like adding an interface onto something that's already been written. If you think back to the Java days, is that apart from the example I've shown, is that often you'd have to expect a type to maybe extend or implement an interface such as comparable in order to use it in a particular function for sorting or ordering, but we don't need to do that. We've got this really nice mechanism here of separating out the type itself from the behavior we need. Okay, so I've got a few other examples that you may be familiar with. So we've got the play JSON reads, and reads itself is actually a type class, and so you start to see functions that are often written like this. I actually pulled this straight off the documentation. So we want to drill through some JSON to a field called name, and then we can call read with a person type. I just made this one up. And then as long as there's a reads type for person, then play knows exactly what to do in order to convert JSON into a person object. So that's really quite nice. And then if you drill down and look at how this is implemented, it's just a function like this. And you can see this is what we've already seen, is that we've got this parameterized on T. It takes a JSON value, but we need to tell the compiler how to go from JSON to a reads. And so we need to provide our implementation here. And if we look in reads, it says what to do for each of the types and things like that, and for each of the JSON types and how to actually go about creating, in this case, maybe a person object. And again, this is similar for writes as well. Okay, another one you might be familiar with, if people have used type level cats or even Scala Z, this library itself is really quite rich and heavy usage of type classes. So having a good understanding of that really does help kind of use the library. So here's one I pulled out here, and I think this probably all makes sense to you right now. Yeah, no. So I purposefully showed this because even if you're not familiar with this, is that really all we want to say here is that in order to use this method, this L type has to have a semigroup instance. And it doesn't matter now if you know what a semigroup is or not. That doesn't really matter. But all we're saying here is that in order to use this, L must be a semigroup. And what you tend to find is the more you start to use mechanisms like this, the more information you can pull out of type signatures here. So maybe you're familiar with semigroups, but not familiar with what a writer T is. But actually, you start to realize that, well, if you know a semigroup is actually just appending things together, and this is a writer, is that, well, maybe this is something to do with what gets written, is that we just keep writing or appending to something. And the nice thing is here is that we're not constrained to be writing to lists or strings or log files or whatever. We can write to whatever we want. And the library has been written so that this doesn't care, and the actual semigroup can be written by someone else. But we just have to have that semigroup instance there, and this will then work. Is everyone with me so far? Or am I losing people? Yes? No? Okay. Right, so I'm gonna make a proposal here, is that I believe that implementing a genetic algorithm is actually a great opportunity to show how type classes work. Okay, so let's talk a little bit about what a genetic algorithm is. So if we look at what Wikipedia says, it's a search heuristic that mimics the process of natural selection. So what does this actually mean? So what we're going to do here is we're going to do the monkeys with typewriters trick, and we're going to write some Shakespeare. So we're going to randomly generate some stuff. We're going to look at the stuff and work out which of the stuff is the best. And then we're going to use that best stuff to seed more generation of random stuff. And then we'll just keep doing this. And as long as we know what's the best, we can always pull that out and use that to create more and more good things. And to be honest, I'm being a bit obtuse here, and I'm trying just to kind of keep this very kind of high level. But we're all here. We know we're talking about genetic algorithms, so I'm going to get into a bit more detail. And then we just keep doing this. We just do this over and over again. Okay. So we need a way to represent stuff. Okay. So I think a good way to do this is a binary string. So we could use some kind of collection, maybe a list or a vector. I've just aliased here to call it a chromosome. So that's the terminology often used with genetic algorithms. And then this, in a bit more detail from that, the algorithm I just showed, is a little bit more detail. So we're going to take some kind of population of these lists of Booleans. And then we're going to inspect them all, and we're going to apply some kind of fitness function. We're going to look at all of these and say, whatever we're trying to do, this chromosome here is actually better than that chromosome there. And then we're going to randomly select some of the inhabitants of this population, respecting the weighting. So a fitter chromosome has a higher chance of being selected than a not so fit one. So we're going to select this mutation pool, and then we're going to mutate it in a couple of ways. So the first thing we're going to do is mate this with another chromosome, and we call this crossover. And then maybe we might take some of the bits from this new binary string, and we'll just twiddle a few of the bits, and we'll see why we want to do that in a bit. And once we've done that, that's our new population, and then we can start again. Okay, so I think the signature for what we're going to write might look something like this. So a population here is just a list of chromosomes, which itself is a list of Booleans. So we need a fitness function. I've parameterized this because we don't know exactly what we're going to be talking about. And then, given a population, we do the steps I just showed, and that creates a new population. So clearly, the fitness depends on what we're actually going to have this algorithm do. We want this to be generic. We want this to work with anything, which is why we've parameterized this. But what we need to do first is we need to convert these chromosomes into real things. We need to look at this and go, well, if we're looking at, I don't know, some DNA sequence for some reason, this one, for what we're trying to inspect, is better than that one. And so we need to actually look at the binary encoding, convert that to what we need to do, and then that's going to make things a little bit easier to work with. So in order to convert this, I think we should have a trait. I've called this genetic. Again, it's parameterized, and it's really just a single function. Given a chromosome, it converts it to whatever we're talking about. So when it comes to us using this iterate function, we need to provide the way of actually converting from a chromosome to whatever we're trying to play with. So I'm just going to make a slight update to our iterate signature here. And so we've got our fitness function, we've got our population, and then we've got this implicit parameter here. And hopefully this looks quite familiar to what I've just shown. Is that actually genetic is a type class? And then we're saying, as long as when we have a fitness function from a certain type, we need to make sure we're able to convert from a chromosome to that type in order to do the comparisons itself. Okay? So the first step that was on that algorithm was to create the mutation pool. If you remember what I said, we're going to randomly select from this population, giving a higher chance of selection to the fitter chromosomes. So if we had a small population like this, and this is completely arbitrary, but here's some binary strings here, and for whatever reason we're looking at here, this orange one is much fitter than the rest of the population. And so when it comes to selecting our mutation pool, you can almost think of this like a dartboard. So we're going to throw darts, and clearly there's a higher chance of us selecting the orange, but the smaller ones also have a chance of being selected too. And so what we'll do for the size of our population, we'll grab that number of chromosomes out here. So this is a small population, we'd only grab 5, but we can imagine there's a high probability here that we're probably going to get 2 or 3 of the orange ones, because they're the fitter ones. But then, for some reason, the blue one might come through as well, just because we're dealing with something random here. So here's some type signatures for maybe thinking about how we'd create this mutation pool. So it's often called a roulette wheel, and so the parameter here is our population, but we've paired it with the fitness function output. And then this returns a function itself. And what this function is, it's normalized between 0 and 1. And so we give it a number between 0 and 1. It works out where on the wheel that comes to and returns that value. This is optional as well because we're dealing with vectors here. We could have passed in an empty vector for some reason, and clearly that would be none. We still want to remain type safe. Okay? So we've got this new property now, and we need to think how we're going to test this. And of course, the correct answer for testing anything in Scala is to use ScalaCheck. And so one thing we need to do is we need to think about a property of this roulette wheel that will hold regardless of what data is there. So ScalaCheck itself is inherently random. And what we're doing here as well is also random. So we need to kind of harness the control somewhere. So we need to find out some property that will always hold whatever the things are in the mutation pool. And so there's just our wheel again. And so here's one I thought of while I was writing this, is that if we create some pool and one of the chromosomes in the pool takes up half the wheel, i.e. it's really, really fit compared to the rest of the population, then when we look at the midpoint, so 0.5, because I said the parameter was normalized between 0 and 1. So when we look at the midway point, that will always return that chromosome. So if we imagine, I don't know, the 6 o'clock on this wheel is halfway, is that when we've got some kind of chromosome that takes over half the wheel, like wherever we look at it, it's always going to be that one. And I think that's a fair property. Okay? And so here's some ScalaCheck code in order to make this work. Are people familiar with ScalaCheck? Are people not? Yep. Okay, for those who are not, it's a property-based testing tool. We provide things that always hold true for our code, and then ScalaCheck will give random data to that property and make sure it always holds true. So what we can see here is we're taking 3 parameters, and we're taking an arbitrary list of measured chromosomes, so that's with their fitness value. I don't care what those numbers are, I just care that they're produced. I'm then asking for a single chromosome on its own, and then another list of measured chromosomes. And what I'm going to say is that for what I've called the lefts and the rights here, if we take their fitness values, add them together, and add 1, then that will become what's going to be the score for our middle chromosome. And then when we put all this together in our wheel, then that value is going to be greater than the sum of everything else combined. And so then we can start to see that hopefully this will always return. When we look at the midpoint here, it will always return this midpoint that we looked for. And then the nice thing with ScalaCheck as well is that this will test for an empty list on the left, an empty list on the right, lots of different permutations. So it's not always going to be the middle of a certain collection. There'll be times where it's the first in the element, times where it's 6 or 7 before it, and things like that. And you start to build up that this is actually doing quite a thorough test of our mutation pool. And we're just holding this single rule that as long as one of the chromosomes is really, really fit compared to everything else, that will always return at the halfway point. Then when we run this, it's great because ScalaCheck runs it 100 times for us and it always returns true. And I'm sure, this is clearly not a comprehensive test. This is not going to make sure that our mutation pool works for everything, but it's more of a, I suppose, an example to show you. And maybe we can think of some more properties, and maybe you could go away and think about how you'd best write these. Okay? So just again, as an aside, what we did here is that we've now got this concrete double value that we need when we're testing this. And so we're going to change our iterate function ever so slightly because we want to pass a function in that gives us a double, because then we can test that with maybe some kind of stream of doubles, and then we can keep calling it with this double value to make sure that it's always getting the right result. But then when it comes to our real full implementation, we could provide an alternative way of providing a lot of doubles. So maybe we'll just change our iterate function to look like this. So we've got our fitness here, and now we've got this function, unit to double. So we can call this, and it will just return doubles for us. And I haven't shown all our tests that I've written here, but if we want to test this iterate function in full, we now have a way to really, really nail down what values we're going to call the mutation function with. And then, of course, when it comes to full implementation, we can just put in the random for next double, and that will just fit nicely into that implementation. Okay, so now that we've got our mutation pool, we need to do this step of what I call a crossover. And what we're going to do, we're going to iterate over this pool, take each chromosome in turn. We'll pick a random one from our original population. On the string of bits, we're going to pick an arbitrary point, and we're going to flip the bits around. So this is often what's called mating, as well as crossover, is that we're taking the two chromosomes together and producing a new one. And so here's an example here. We've got a couple of chromosomes. We just pick some random point during along the string, and then we flip these bits around. You can see we're just flipping them. And then we don't care about the one from the original pool. We're only now looking at the mutation pool. This is what we selected for based on the weight. And so the ones with a higher weighting should have had a higher chance of getting into this pool. So we can just throw that one away. And now we've got a new chromosome. And now we need to think about how to test this as well. And again, we can do this with ScalaCheck. And this one's a bit more gritty. So here's one thing I think, is that if we provide two or three fragments of a chromosome, we can then work out where that crossover point is. We can provide that chromosome to our algorithm, and then that should get swapped in the right place, and we know what should come back. And so our test is a bit more involved, and it looks something like this. So we have a number for the point on the string where the crossover will happen, and then this number here is just the length of the string after the crossover point. We have a function here which generates some pairs for us. So it provides a chromosome for us into split parts. So we know which part is before the crossover and which part is after. And then our property here takes two split chromosomes, it puts them straight together and calls this crossover method. And we know this crossover point because it was generated from our original property. And of course, we know what the expectation should be because we broke it up, and we know where the crossover should happen because we have this value here. And then we can see here that passed. Does that make sense? It's quite involved. It's it's a bit fiddly, especially if you're not too familiar with ScalaCheck. But basically, we've got 2 chromosomes that are broken in 2. We pass them in, and we know where the flip will happen. And this is really nice because this shows that our crossover is working quite well. And again, notice here that this is not for a specific length of chromosome. This will be testing it for any length. And also the crossover point will vary within that length. So it's getting quite a thorough test here. And again, like the aside I said before, we need to add a new function onto our iterate method because now we need to have a little bit more control over where our crossover point is. So when we're testing it, we might want to find a string of integers to test where that happens. But then again, when it comes to our full application code, we can just put in the random next integer value. And then finally, there's one more thing we were to do, and that's random mutations. And what we want to do here is take our string and in a few places just flip the bits. The reason we want to do this is that we might find that our algorithm is actually homing in on what's called a local maximum, and that we're getting quite close. But because of the way the algorithm works, there might be a much more optimal solution elsewhere that we can't see. And so by flipping some bits, we might jump to a different area of the solution space, and then we might find that actually we're in a much richer environment, and then we can start to home in on that instead. And so we're just going to select a few bits to flip, like so. And I'm not going to show the test for that, because I think that should be quite straightforward from what I've shown as well. And we're done. We can ship it. And so our final iteration signature looks like this. So we added those two functions I mentioned. There's also a next Boolean as well, because we maybe don't always want to do that mutation. So we'll call this next bool. If it's true, let's do some mutations. We can draw some integers from next int. Otherwise, we just won't do it. And just coming back to thinking about type classes, as long as there's a genetic type class for our type, we can provide a fitness function for that type, and this will run. And that's really quite nice. So you might be able to think of some algorithms that I haven't thought of, and as long as you can provide a type class and a fitness function, this thing will just work. Okay, so I've spent half an hour defining things. Let's have a look at this in action. So one thing we can do is we can find the optimal solution to a function. And I'm going to provide a really, really basic function to start. So it's clear, that we could maybe use a genetic algorithm here to pick maybe some random integers, apply this function to those integers, and the fitness function should be quite clear that we can just call it with that. And the higher the number, the more fitter it is. Okay? And so this graph is our fitness function. So all we really need to do is just provide a way to turn the binary strings into numbers, and hopefully this isn't too complicated. We just spin over our vector, and we shift our collection of we shift our accumulated number each time, and if it was a true at the time, we add 1, otherwise not. And so we see some results like this. Is that visible? It's not great, is it? Sorry. And so I ran the genetic algorithm looking to target this number here, and you can see early on in the implementation, the population is all over the place. It has no idea, and it's swinging down and up, and there's quite a wide variation in the size of the population. And then, I don't know, but something happened here, and then we managed to home in quite close to this value. And then the red line here is the average. So clearly the average is all over the place here. And I think we tend to get a little bit closer to the target at the end. Maybe if I'd run this a little bit longer, it'd be a bit clearer. And if we just zoom in on that flat line, we can actually see it's not so flat. So even though we're getting closer, there's still quite a bit of variation and noise. And I did this again, just with another number, got similar results. And this was with a population size of 30 for 1,000 iterations of this algorithm. Okay? So let's have a look at maybe a slightly more interesting implementation. Maybe do some modern art, maybe some computer-generated pictures. So remember what I said is that this type class, it's not restricted to any particular values. Like any type that is available in the JVM, written by anyone at any time, can, as long as there's an implementation of genetic for that, this will work. So what about creating one for this, a Java image, okay? And so what we could do here is our genetic implementation. We'll use this chromosome binary and we'll encode the data for, say, 50 triangles. And we'll give them XY coordinates and we'll give them colors. And then that should be enough maybe to create an image. And so assuming that the image we're going to build is this size, then we're going to need 60 bits per triangle just to locate the coordinates for the 3 points on the triangle. And we're going to need another 24 bits to represent the color of the triangle. And then we'll take another 24 bits on its own just to have a background color for our image. So if we're doing this with 50 triangles, that's just over 4,000 bits. It's like the values we were looking at earlier for the numbers on the graph, I think that was 16 bits. So we've kind of gone a little bit through the roof here with the number of bits. So we need to think about this fitness function. So, well, what does it mean for an image to be fitter than another one? It's quite a subjective thing, really, isn't it? You know, if we look at two images, what's the better one? Well, what we could do is we'll just compare with an image that already exists. And then if we take an image, we can maybe work out a value, how close that is to a particular image. And so I zoomed in on a particular famous piece of art and thought that might be quite a nice one to use. And so you need to think about the fitness function for this. So a poor man's image comparison, and this is just a discipline in its own right, comparing images. So this is definitely not the best or the most appropriate way to do this. That given both images, so the zoomed-in Mona Lisa and our generated image, for each pixel, diff the RGB values, sum all these diffs, the one with the smaller value is the fitter image. Clearly, this is not the best. You know, clearly there's lots of ways to do this, and there's pages and pages on Stack Overflow of people who've put a lot of effort into image comparisons and stuff like this. But we still have, regardless of the efficiency of this, we still have another problem as well, is that the parameters to our iterate function don't compare things to themselves. It's literally A to long. So in this case, buffered image to long. So there's a bit of a problem here, is that we need more information. But of course, this comes really easy in Scala because we can just curry this. So if we have a function like this, we can just provide the Mona Lisa as this first parameter, and that gives us a function from buffered image to long. And then we can just set this as a base image and put that into our iterate function. And then when we're generating these images then, is that we're really just comparing it to this base image. Okay? And so here's some results. This is something I did a couple of weeks ago. So, yeah. So that was 1,000 iterations on a population size of 30. Okay. So then that's 2,000. Oh, background's changed. It's getting a bit closer. A bit more yellow. Look, you can see, look, it gets a bit darker in the corners as well, which is quite nice. So that's 5,000 iterations. It's 5,700 iterations. And that took me 3 days. So, yeah, I mean, clearly, you know, dealing with this number of bits and doing not the most efficient comparison of the images took a little bit too long. And my algorithm was never written to kind of consider doing things in parallel. So one thing I'm considering doing is kind of taking this away and tweaking it somewhere. But I feel that's progress. What do you think? Yeah? Yeah. So, yeah, that was a lot of electricity to do that. So that's about all I really had time for here. So just a few things to kind of wrap up. Yeah, they're not efficient. Like, it's not the best way to do things. There are scenarios where genetic algorithms are great, where maybe the domain of a search space isn't very well understood. But I just thought it's going to be a bit of fun here. But what I do like is that typeclasses here provided a really neat interface to our algorithm. Like, the algorithm for the two examples I showed was exactly the same. The code did not change between them, and all I had to do was provide the fitness function and provide a way to show what the encoding of the binary string meant, and that was it. And another thing that was really nice is that we got this inherently random tool, ScalaCheck, and we've got this inherently random problem that we're trying to solve, and we're able to use it in a deterministic way for what really is a non-deterministic problem. And so, well, what else could we use genetic algorithms for? So these are things I just thought up off the top of my head. We could write code, yeah? If we wrote some unit tests, things that passed and failed, we could just let it go and create maybe an abstract syntax tree and see how it comes out and things like that. I don't know, maybe it'll do us out of a job or something. I found this really cool thing on the internet, racing cars. I think this is written in JavaScript, basically, and it's kind of the algorithm here then is used to encode the cars, and they're given weights and shapes and stuff, and the road is random, but for each iteration the road stays the same, and hopefully this car will crash in a minute, and then it starts again, and then you start to see that and you can leave this running for hours, and the cars get really good, and they work out how to get over this kind of stuff. And so you see, look, this is quite a similar car to the one that just passed it, and you can see, look, I think that's the ghost in the background. But anyway, we getting a bit sidetracked, I think. But, yeah. And I mean, I suppose the world's your oyster, really. A game-playing bot, maybe write something to play poker or something like that. Maybe you can think of your own. So yeah, that's all I had time to talk about, really. I put a few links up here. This talk was originally inspired by a blog post I saw of a guy who did the Mona Lisa. He did it in C#. It technically wasn't a genetic algorithm because it was purely random and just flipping bits. There was no concept of a mutation pool or things like that. This book here is kind of the de facto Bible for genetic algorithms, and it was written in the 80s. And then I've put a link up here to all the code from my talk, because I didn't even show the implementation of my algorithm. I didn't think that was kind of the interesting stuff to talk about. But it's all up there, and I'll send the link round for these after the talk. So yeah, that's all I had time to talk about. I hope you enjoyed it. If you have any questions, please shout out. I think there's a microphone.
Does typeclasses fill the role of something like a decorator pattern? And if it does it have any disadvantages over a decorator pattern?
I think, so the question was, does typeclasses fill the role of a decorator pattern? That's right. That's not something I've thought about before, really. I don't think so. I see, I suppose, a kind of one-liner for what typeclasses are in my head is really a way to add your own interface onto someone else's class. So, I mean, they decorate the type, but it's clearly not the OO decorator pattern. I think they're completely separate. Yeah. Mm-hmm. Got a question here? You can shout it out. I'll.
How'd the other person do?
Really well. Much better than me. Much better than me, but it wasn't a real genetic algorithm. Yeah. So do you want? No, I won't show it because it's better than mine. So, but seriously, I'll send this round or Google Mona Lisa genetic algorithm. It's like the top hit. So, anyone else? Yeah, there's a question at the back there.
It was more of a comment or a
Okay.
plug, if you don't mind.
Yeah, yeah.
I'm actually in the middle of writing a genetic algorithms framework
Okay.
in native Scala, because there exists some for Java. And my first iteration was doing it with traditional inheritance, but I've since moved on to the type class pattern, so I totally agree with you that it's
Great.
a
That's good
great,
to hear.
a great
Good to hear
fit.
I'm doing it right. So.
Yeah, so if anybody feels particularly inspired and wants to help, come find me, and we can
nice.
talk about genetic algorithms all day.
That's really cool. I think I saw another hand somewhere a minute ago. No. No. Okay, all right. Well, thanks again for coming along, and I hope you enjoyed it. So.